Father, we thank you for today. Thank you for your mercies. Thank you for your love. Blessed be your holy name. As we start, Holy Spirit, we pray your presence start with us. Give us understanding, O Lord. In Jesus' name.
Amen.
All right. I give you an assignment you have not submitted.
Yes.
Was it difficult?
No.
So what happened? What happened? But have you done it?
I was having the I'm not finished. I was having PSAT practice test, so I
So
was
we're having
preparing
what?
for the PSAT practice test.
Okay.
So I was preparing for it because you wrote it this morning.
Okay, you wrote it today.
The practice test, but the main exam is in October.
Okay, but the practice test, you wrote it today?
Yes.
Okay. Online, right?
No, went to school.
Oh, really?
Yes.
Okay. Your physics teacher is Mr. Emmanuel, right?
No.
But you know Mr. Emmanuel?
Yes.
So who teaches you physics then, if it's not Mr. Emmanuel?
Mr. Wale.
Okay. But I guess Mr. Emmanuel is the HOD or Mr. Wale?
Yes.
Okay.
Mr. Emmanuel.
All right. I guess I know him. We have met. All right. Let's look at this. I'm going to share my screen now. The assignment, probably we might just have to coming. Might just have to share my video. Share my screen, sorry. I guess this is the assignment I gave you.
Yes.
Okay. Now, all right. We have a question here. Nitrogen reacting with that's 1 molecule of nitrogen reacting with 3 moles of hydrogen, giving you ammonia. All right. Don't forget our laws. Now, our aim is to determine where equilibrium will shift to. Now, they said when we add, and that's to the reactant, equilibrium will shift to the right, that's this. And then H2 decreases, ammonia increases, this remains the same. Okay, what I'm just interested in equilibrium shifts. Don't worry about this other part. I'm just concerned to where equilibrium will shift to. Do you understand that?
Yes.
Okay. Now, what happens when we add H2? That's hydrogen. Where would equilibrium shift to?
To the right.
Right. Okay. What if we add, this is NH3. This is NH3. What if we add NH3, where will equilibrium shift to?
To the left.
To the where?
Left.
To the left. What if when we remove N2, where will equilibrium shift to?
To the left.
Eh?
To the left.
To the left. Why?
Because this will lose.
Sorry? Hello, sir.
reactants. There are less reactants in the
Sorry, I didn't get that, please.
because there'll be less reactants in the
Okay. Okay. Okay, we said when you move N to equilibrium, we shift to the left, right?
yes.
Okay, what about when we remove hydrogen?
It shifts to the left.
Okay. When we remove NH3,
To the left.
to the
Okay.
left, why?
Because when the products reduce in
So where is it
the less
going to? Come on.
okay to the right.
And where is it going to shift to?
To the right.
To the right. Why now?
Because decrease in concentration of products will cause the equilibrium to shift to the right.
Okay. I wanted you to really know that. Okay. Increase temperature. Oh, we've not discussed temperature. Okay, let's take temperature out of it. Increase in pressure. Where will equilibrium shift to? Increase in pressure. Look at the pressure. Where will equilibrium shift to? Increase in pressure.
To the right.
Why?
Because the right has fewer moles.
Good. And decrease in pressure. Where will equilibrium shift to?
The left.
Okay. Awesome. Awesome. Now I gave you this also as an assignment, so let's use it as classwork then. Add Na, that's sodium hydroxide. Where will equilibrium shift to?
To the left.
To the left?
Sorry, to the right.
To the right. Look at this thing very well. Look at the equation very well. Okay. Now, I know you're looking at somewhere. You're looking at those what do you call it? Those things I gave you then. I know that's what you're using to get this. When we get to the main classwork, you won't have to look at it now. You have to know it on your own. Okay. Add NaCl, which increases sodium ions. Adding sodium chloride, which increases sodium ions. So where will equilibrium shift to?
Um, add,
Where will the equilibrium shift to?
left.
To the left. Awesome. Now, add KOH, potassium hydroxide, which increases hydroxide ion. Where will equilibrium shift to?
To the left.
Okay. Add hydrogen ion, which decreases hydroxide ion. Where will equilibrium shift to?
To the right.
To the right. Good. Okay. Let's come to increase in pressure. Okay, increase in pressure. Where will equilibrium shift to?
To the left.
Correct. And decrease in pressure to the right. Okay. Awesome. I still have other questions though. So I would have to get those questions out. Where are you? Come here. Good. Where are those questions? Oh, it's almost the same thing. Are you serious? Come on. These questions are almost similar. Are you seeing this? Can you see this? Can you see this? Hello, can you hear me?
Yes, I can see it.
All right. Now, look at this. We said, look at what happens here. That when we add nitrogen, nitrogen here remains the same. Hydrogen decreases. This one increases. And the equilibrium constant remains the same. I think I should give you this as I'm going to give this as classwork later on, but I would want us now to treat. I would like us now to treat temperature, effect of temperature. I doubt we did not do temperature the last time we met. So when we're talking about equilibrium, we did not look at if there's factors affecting equilibrium of a chemical reaction. Remember Le Chatelier's principle, which we said that when an external constraint such as change to temperature, pressure, or concentration is superimposed or imposed on a chemical system equilibrium, the equilibrium will shift so as to annul or neutralize the constraint. That says, in a simpler term, that when a system is stressed, the equilibrium shifts so as to neutralize that stress. That's just a simple way of saying that. Now let's look at effect of change in temperature. Effect of change in temperature. All right. I want you to know that increase in temperature of a system will shift the equilibrium position to backward reaction. Increase in temperature. Are you writing that?
Yes.
Increase in temperature will shift the equilibrium position to backward reaction. That means what I'm giving you now, for when we talk about increase in temperature, we should understand, the first thing you should note is, just the way when we talk about pressure, what's the first thing you should note when it comes to pressure? Can you remember the first thing I said you should note when it comes to pressure?
Increase in pressure is decrease in volume.
Okay, it means decrease in volume. There's another thing again I asked you, I said, whenever it comes to pressure, there are some things we should note. I told you, number one, you should note if it is in a gas medium. If it is in a solid medium, there will be no effect of equilibrium, right?
Yes.
I also told you that when you talk about increase in pressure, you should also note, you should also be familiar with the number of moles. The number of moles will determine what increase in pressure, where it will shift the equilibrium position. The same thing for temperature. When we are talking about temperature, we should understand if it is an exothermic reaction or an endothermic reaction. You must know if it is an exothermic reaction or an endothermic reaction. Now, if it is an exothermic reaction, increase in temperature will shift the equilibrium position to backward reaction. We shift
If it's an exothermic or endothermic.
as if it's an exothermic reaction. Increase in temperature will shift it to a backward reaction. We shift the equilibrium position to the back and decrease and decrease in equilibrium, we shift it. Decrease in temperature, we shift the equilibrium position to the right. Okay, before I go further on it, I would like to show you a video what I'm trying to talk about. Okay, I guess we are ready. Let's look at this, please. All right, I guess it's coming up. Okay, now I said, remember what we said, that before you can start determine the reaction is that's increase in temperature. You must first determine the energetics of the reaction. That means that you should check your delta H, your enthalpy. If this enthalpy is minus 75 kilojoule, if this is minus 75 kilojoule, this means that the forward reaction is exothermic, right? The forward reaction is exothermic. That's actually what it means.
Yes.
And that means that the backward reaction is endothermic, isn't it, right?
Yes.
Okay. Now, what we are trying to say is that when you increase the temperature of this reaction, what happens? Increasing the temperature of this reaction favors the forward. Increasing the temperature of this reaction favors where the forward reaction. Now, increasing the temperature, when you increase the temperature of this reaction, actually what happens is that the reaction is favored. It's actually favored. So let's look at this, please. Oh God, what's happening? I'm coming.
The imposed stress. Decreasing the temperature would cause the forward reaction occurs, 75 kilojoules of energy is released, and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress.
Now, what just happened now is when you increase the temperature, what happens at this point is that, remember, the forward reaction is already exothermic. This one is exothermic, and this is endothermic. Now, and this is an exothermic reaction because of this heat. Now, when we increase the temperature, remember this reaction, heat is released, or in an exothermic reaction. When we increase the temperature here, it favors the backward reaction. It favors, what happens, equilibrium will shift to favor the backward reaction. The equilibrium will shift so as to favor the backward reaction. So the equilibrium will shift to the left to favor the backward reaction. Why? Because we have minus 75 kilojoule is being given out. So what happens at this point now is the equilibrium will shift so as to neutralize it, bringing back 75 kilojoule. So the equilibrium will shift to the back to favor more formation to favor the backward reaction. That means more reactants will be formed if the backward reaction is favored. Do you understand that part?
Yes, sir.
Now, but if we reduce the temperature, now if we decrease the temperature, what happens now? As we are decreasing the temperature, that means minus 75 kilojoule, it's, instead of being given out now, like before, now minus 75 kilojoule is coming back. 75 kilojoule is coming back to the system. So the equilibrium will shift to the right to favor the product. So decrease in temperature causes the equilibrium to shift to the right, thereby favoring the forward reaction. That means more formation of product. More formation of product. The same thing with your rice or your indomie. You are cooking your spag. You're cooking your spag. When you increase the temperature, because you're increasing the temperature, you are producing more product. That means increasing the temperature means that you want your product, your spag, your cooked spag, to be formed. So what happens to equilibrium? Equilibrium will shift to the left, favoring more formation of reactants. Why? Because increase in temperature already makes more products to be formed. So in order to counteract that stress already, equilibrium will shift to the left to favor more reactants, so that more reactants should be formed. Now, when you reduce the temperature, you know definitely now when you are boiling your indomie or whatever, when you reduce the temperature, you know definitely that the reactant, which is the raw indomie, will still be there for some time. So what happens? Equilibrium shifts to the right to favor more of the product. But remember, that is for an exothermic reaction. I hope you understand that.
Yes, sir.
All right, let's continue with the video now.
Decreasing the temperature would cause the system to produce more energy. Therefore, the exothermic reaction would be favored. The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction. Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless. What observations do you think can be made when the temperature is decreased? How about when the temperature is increased? Please pause the lesson to think about this and resume once you are done.
Okay, I want us to think about this.
A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced.
I hope you understand that.
Yes.
That a decrease in temperature favors the exothermic reaction. That means favors the forward reaction. Favors the forward reaction means favors the product, more formation of products.
Yes.
So don't be confused when they say it favors the exothermic reaction. Means it favors the forward reaction. Means more formation of products.
Yes, sir.
Okay.
Since it is a colorless gas, the mixture should appear paler. An increase in temperature favors the endothermic reaction, so more nitrogen dioxide is produced. The mixture should therefore appear darker brown. Addition of a catalyst does not affect the position of equilibrium as it increases the rate.
Did you write that? That was very, very instructive. Catalyst.
Addition of a catalyst does not affect the position of equilibrium.
The addition of catalyst does not affect the position of equilibrium. The addition of catalyst does not affect the position of equilibrium. Have you written that?
Yes, sir.
Okay.
Darker brown. Addition of a catalyst does not affect the position of equilibrium as it increases the rate of both forward and reverse reactions. It only quickens the attainment of equilibrium. Let's return to the...
Okay. Remember, addition of catalyst does not affect the position of equilibrium as it increases either the forward reaction or the backward reaction. That means more formation of reactants or more formation of products. one thing we know about catalysts from what we did in rate of chemical reaction is that it helps in attaining, it helps to attain more, that's the state of equilibrium, thereby reducing the activation energy. So we should note that about catalysts.
Example of you digging a hole and your friend refilling it while you dig. Imagine that you are both given much larger shovels. The size of the hole still remains constant, but with each dig or fill, more soil is removed or filled. In conclusion, when the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature of a system at equilibrium is decreased, the exothermic reaction is favored. Adding a catalyst, no effect on the position of equilibrium.
Okay. Wow, that's awesome. I think we have 2 more videos to go before we go into practicals of effect of temperature.
Professor Dave here. Let's talk about.
I'm coming, please. I guess we need to just look at this.
Le Chatelier's principle.
He knows a lot about the science stuff. Professor Dave explains.
Le Chatelier's principle says that if you induce a stress on a system at equilibrium, the equilibrium will shift so as to relieve that stress. So let's see some examples of a stress we could put on a system at equilibrium. First, we could modify the concentration of any of the compounds. Let's say we add some of this reactant. That will unbalance the equilibrium, and the forward reaction will speed up to use up some of the additional reactants, turn them into products, and restore equilibrium. The equilibrium is said to have shifted right. If we add more products, it would shift left. Likewise, if we selectively remove one of the components, the equilibrium will shift to produce more of that species to restore balance. That is one type of stress we could put on a system. Another stress would be to change the temperature. To see how this would affect an equilibrium, we have to see whether a given reaction is exothermic or endothermic. This tells us whether a reaction absorbs or releases energy, and is signified by delta H, the change in enthalpy. If delta H is negative, the reaction is exothermic and releases energy. So we could think of heat energy as a product of this reaction. If instead it's positive, that means it's endothermic, and energy must be absorbed for the reaction to go. So we could think of heat energy as a reactant in that scenario. Once we translate thermochemical data in this way, we can treat the word heat as just another substance involved in the reaction. Higher temperature means more heat, so things will shift to the other side to use up some excess heat and relieve the stress. Cooling it down would have the opposite effect. The third stress we can examine is changing the volume or pressure. Let's say the equilibrium involves gases in a balloon. What if we decrease the volume? If we remember Boyle's law, we know that the pressure will go up, since the smaller the volume, the more the particles will hit the sides and exert pressure. If there is a discrepancy in the number of moles of particles on either side of the equilibrium, it will shift towards the side with fewer particles so as to alleviate some of the additional pressure. In this equilibrium between a diatomic molecule and 2 monoatomic species, the right side has twice as many particles. So shifting left means atoms fusing together, resulting in fewer particles, which lowers the pressure on the container. If we increase the volume, thereby lowering the pressure, the equilibrium would shift towards the side with more particles in order to regain some of the lost pressure. Let's check comprehension.
Okay, let's do this. I need you to tell me your answers. I need you to tell me your answers. Sorry, what did you say, please?
When more H2 is added, equilibrium shifts to the left.
Equilibrium shifts to the left. Okay, what about this?
To the right.
The increase in temperature.
To the right.
Okay, the volume is reduced.
To the left.
I'm actually writing it here so that when the answers are being pasted, we would not, it won't be conflicting.
Okay.
All right. Let's see how correct you are. Good. Wow, she's correct. Keep clapping, keep clapping, keep clapping, keep clapping, keep clapping. Awesome. You're not clapping. You don't know clap. I'm not hearing the clap. Who is doing that, please? Ifoma, give her more light. Give her more light. Wow, she did well. Give her more light. Ifoma, more light, please.
She has gone.
She has gone. Okay, awesome. Now, that's a good one. When we know definitely that this is an endothermic reaction because it's 187. So now we're not saying when the temperature is increased, that means we are increasing the temperature. And remember that the left reaction is actually the exothermic reaction. So increasing the temperature, that means we are having more heat being involved. Now equilibrium shifts to the right to favor the endothermic reaction. Awesome. And the other one for volume, reduced volume is the same thing as increase in temperature. So equilibrium shifts to the left, to the place with fewer moles. That's awesome. Okay.
Thanks for watching.
All right, now that you've known this, let's go to the real practical. Now. Let's go to the real practical. When we get to see, we've been talking about these reactions in A, B, C, D. Now let's get to see this reaction in real life. Let's get to see them now when they are being reacted, all right?
We are now preparing NO2 by reaction of sodium nitrite with concentrated sulfuric acid. So here
Remember she said sodium nitride.
This flask added sodium nitride, and we are going to add to it concentrated H2SO4. When this reaction happens, a gas is formed, which is NO2. So as you can see here now, the gas started to form. This is the NO2 gas. Now this gas, it undergoes another reaction. NO2 plus NO2, it gives N2O4. Now the NO2 has a brown color and the N2O4 has a colorless, it is colorless. And this reaction is exothermic. So now we are, after attaining equilibrium, we are going to study the effect of temperature first and then the effect of pressure.
Remember they said it's an exothermic reaction. So much heat is actually released in this reaction. Okay.
Here you can see two beakers. This is filled with cold water and this is filled with hot water. Now when we insert this flask in the cold water, the color becomes more to the colorless.
Light brown.
Yes, light brown color. According to this reaction, when we remove heat, the equilibrium will shift again to give me more N2O4. It will go to the right. Now, if we add this flask and put it in the hot water, the equilibrium will go backward toward more NO2. So the color should be more brown.
Awesome. Do you understand what's happening?
Somehow.
Eh?
Somehow.
Okay. The cold water means it's reduced temperature, because cold water now is a decrease in temperature. Now, when is an okay? I need you to know this now. It's something you know. When we have decrease in temperature, where will equilibrium shift to if it's an exothermic reaction?
Decrease in temperature.
Yes, where will equilibrium shift to?
To the product.
To the product. So, and remember the product in which she showed us is that it will give us a colorless solution, because this is N2O4. Now, coming to the hot water is increase in temperature. When we have increase in temperature, where will equilibrium shift to?
Increase in temperature to shift to the reaction.
To the reactant, to the left, which is now the color, that's the brown color. So that's exactly what she's showing us there now, that this is actually attaining equilibrium. Now, she placed these volumetric flask into the cold water. Because of equilibrium, what we said, the color became colorless, showing you that it was giving more of the product now. But when she kept it in hot water, we have more of the equilibrium shifts back to the left, favoring the reactants. Do you understand that now?
Yes.
Okay, I'll just go back a bit.
If we add this flask and put it in the hot water, the equilibrium, the color becomes the effect of temperature first and then the effect of pressure. So here you can see two beakers. This is filled with cold water and this is filled with hot water. Now when we insert this flask in the cold water, the color becomes more to the colorless. Yes, light brown color. According to this reaction, when we remove heat, the equilibrium will shift again to give me more N2O4. It will go to the right.
So this is the increase in temperature giving the products now shifting to the right. Now it is almost colorless. If we keep this in more in cold water, it becomes colorless. Now she wants to increase the temperature, thereby putting it in hot water.
Now if we add this flask and put it in the hot water, the equilibrium will go backward toward more NO2. So the color should be more brown. So when we remove it from the cold water, it is less brown. When we're in the hot water, sorry. When we put it in the hot water, it is more brown. When we remove it, it is lighter. Okay. Now, the second effect is pressure. So here we have a syringe. We are going to open this flask and try to trap this gas inside the syringe. So as you can see here, we're filling the syringe with NO2 gas, which is brown gas. Now again, if we look at this reaction, when pressure is added, when more pressure is added, the reaction.
Now, when increase in pressure, where do you think its equilibrium will shift to here?
To the left.
Increase in pressure, where will equilibrium shift to?
To the left.
Really? Are you sure? Are you sure?
Okay, sorry, to the right, to the right.
The place with fewer moles, that's to the right.
Yes, sir.
Okay, and decrease in pressure to the left. All right.
Reaction will go toward N2O4. And if we put less pressure on this reaction, it will go back to NO2. Here, more pressure, the color starts brown, of course, because the concentration of NO2 increased.
I did also charge my computer.
All right.
To NO2.
Now look at something she's doing now. She's increasing the pressure. You're going to have more, the way she's increasing the pressure now, you will see more brown colors will be formed. This is showing you that more NO2 gas is being formed. More pressure. The moment she's increasing the pressure with her hand from here, the moment she decreases the pressure, thereby releasing it out, you will see that it will be lighter brown. And if she keeps decreasing the pressure, it becomes colorless. So let's see that now.
Here, more pressure, the color starts brown, of course, because the concentration of NO2 increased, and then the brown color become more and more faint and light. Here we're pressing again, and the color of NO2 starts brown and then goes faint. Yes, and when I release the pressure for less pressure, so this means that I have more N2O4, and then the color becomes again brown.
All right, this is beautiful. This is beautiful. We've just seen a practical illustration of what shows that. Now, the last thing I'm going to be showing you on this, it's let's see one more practical, then we can continue.
Okay, in this video, we're going to look at a important part.
Sorry, I'm coming. All right, let's see this one. Can you see this, please?
Yes.
Okay.
Okay, in this video, we're going to look at an important part of chemistry called Le Chatelier's Principle. And this is all about reversible reactions when they're at a state we call equilibrium, if you like, when they're balanced. And Le Chatelier said, when a system, that's any group of chemicals together in a test tube or a flask, when a system in equilibrium is subjected to a change, the equilibrium will shift to minimize that change. And hopefully the experiments I'm going to show you now will illustrate that particular principle. Now, on my left, I've got a chemical called, well, it's it's cobalt chloride, but it's dissolved in water. And cobalt chloride in water produces a pink solution due to a cobalt ion, which has 6 water molecules bonded to it. You don't need to know that formula at GCSE. At A2 you do, but that's another story. Meanwhile, on the right-hand side, we have a beaker full of cobalt chloride complex. It's a nice rich blue color. In the middle, a purple color, we've got an equilibrium of the 2 different chemicals mixed together. So you've got some pink and some blue, just like when you used to mix paints when you were younger. We've got a nice purple color. Now, let me illustrate Le Chatelier's principle. I've got some hydrochloric acid, and I'm going to put a few drops of that into my beaker in the middle that's at equilibrium. Hydrochloric acid, being an acid, it's got H+ ions, and being hydrochloric acid has chloride ions as well. And this being concentrated hydrochloric acid, we're adding a large number of chloride ions. And watch what happens. You see the solution goes blue. If I stir it round, it's not fully blue, but it's gone a darker purple, a bluer purple. And if I keep adding hydrochloric acid, you can see a very intense blue color there. Eventually, we will get to a complete blue. We're not quite there yet. We've still got some water present. So we've got the pink chemical and the blue chemical. They're still in equilibrium now, but there's more of the blue, less the pink. Because we added more chloride ions. It says in Le Chatelier's principle, when a system in equilibrium is subjected to a change, the equilibrium will shift to minimize the change. We added lots of chloride ions. So the equilibrium shifts this way towards the blue end to get rid of some of the extra chloride ions we added. Those chloride ions we add, some of them will react with the pink to make more blue. Now, we can reverse that reaction because we could add some water. Now, if I just get a beaker of water, if I add a bit of water back, so we're adding something now to the right-hand side, we're increasing the amount of water in our system. Just pour in some water, and straight away, you can see pink, and didn't take much water. We've already gone back towards the sort of purple color we started off with, and we're very close to the pink. So that's one thing we can do. If we add more of the chemical on one side, on the left, more chloride ions, it shifts towards the bluer side, it goes to the right. If we add more water, it goes to the left. And that is Le Chatelier's principle in action. There is another important thing to notice with Le Chatelier's principle, and that's the effect of temperature. Now, if I just move my blue chloride substance and my pink water substance out of the way a minute, I'm going to take my mixture here, and I'm going to put it in 3 separate boiling tubes. And I want about the same amount in each. Try and do a fair test. I'll show you in a second that they look pretty much the same. It doesn't have to be exactly the same. There we go. Similar amounts of 3 purple solutions. And I'm going to put one of my solutions in ice. So in it goes. I'm going to leave one of my solutions at room temperature. And in my third solution is going to go in water that I boiled a couple of minutes ago.
Remember, what we are trying to see here now is the effect of temperature. In ice means you are decreasing the temperature. In not putting that in any, whether water or anything, that means you're keeping it at room temperature. and now you're using the hot water, increasing the temperature. I hope you understand that, right?
Yes, sir.
Okay.
Let's see if we can spot any difference. So we'll give them a few seconds to shift. Remember what we've done. According to Le Chatelier's principle, if we subject an equilibrium to a change, the equilibrium will shift to minimize that change. So if I heat something up, it will go in the direction that tries to cool it down, and that is the endothermic direction. If I cool it down, it will go in the direction that tries to warm it up.
Wow.
Exothermic direction. So Le Chatelier's.
Now this is it. This one has become more pink. Okay. This one has become more blue. This is awesome.
Principle is a bit like Salt's law. If you try to do one thing, the chemicals will try and do the opposite. I try and heat it up, the chemicals will go endothermic, they'll try and cool down. If I cool it down, they'll try and go exothermic, they'll try and get hotter. Okay, they've been in the beakers for long enough now, and if I take them out, okay, the difference between the one on the left and the middle isn't that great, but the one on the right you can see has gone very blue. So, when I make the chemical very, very hot, that was the boiling water out of the kettle, it goes in the blue direction. When I make the water very, very cold, it tries to go back in the pink direction. So this tells us something important about our reaction. Let's just recap then. Heated up, it goes blue. So with heat, it goes in the blue direction. So going to the right, making the blue chemical, must be endothermic. And when I cool it down, here's in ice, here's at room temperature, it becomes more pink. So when I cool it down, the equilibrium shifts to try and warm up, it goes in the exothermic direction. So we can use Le Chatelier's principle in more than one way. If we know whether a reaction is exo or endothermic, we can predict which way it will go.
Okay, awesome. Now, the first thing I gave you, that increase in temperature, we make it go to the, that's the backward, we favor the backward reaction, which is the reactant. Remember, that was in exothermic. That was in an exothermic medium. But in an endothermic medium, when you increase the temperature, you can see what is happening there. Increasing the temperature makes it go endothermic. That means favors the forward reaction. And decreasing the temperature makes it exothermic. I hope you understand that.
Yes.
So this is now for an endothermic medium. This is for an endothermic medium. So when you increase the temperature for an endothermic medium, it favors the forward reaction, which is, it favors the forward reaction, which is more formation of products. And when you decrease the temperature, it becomes exothermic.
If we don't, we can do the experiment and we'll see which way it goes, and that will tell us whether it's exo or endothermic. But this idea applies to all reversible reactions. If you heat any reversible reaction up, it will shift in the endothermic direction. Cool any reversible reaction down, and it always goes in the exothermic direction. And that's it, Le Chatelier's principle in a few simple experiments.
All right, awesome. So I believe now we have a thorough understanding of this topic. Now this has really brought in our knowledge on this. The next thing we need to understand is, remember we said a catalyst has no effect on equilibrium position. Rather, a catalyst will make the equilibrium to be attained faster. All right, you wrote that, isn't it? Hello? I was saying something on equilibrium. I said that catalyst has no effect on equilibrium. That's on the position of equilibrium. Rather, it makes equilibrium to be attained faster. I hope you wrote that, please.
Yes.
Okay. Now, the next thing we want to look at is equilibrium constant. Equilibrium constant. Okay. There's something, equilibrium constant is written as K, capital letter K subscript C, and there's a law known as the law of mass action. The law of mass action states, please write this. The law of mass action states that at constant temperature, the rate of reaction is proportional to the active masses. At constant temperature, the rate of reaction is proportional to the active masses. That means you put in brackets, concentration raised to the power of its coefficient. Concentration raised to the power of its coefficient, close the bracket, of each of the reactants. Of each. Okay, I'm going to give you an example of what I mean. In this case, let's see this example. For example, if we have A plus now what are we trying to say? The small letters denote the number of moles. That's maybe 2, 3, 1, stuff like that. Now, how do we get the equilibrium constant? Now it becomes, getting the equilibrium constant becomes C, and it becomes the small letter C, that's the mole, and your D, okay, over your A, and then your B. The equilibrium constant. All right, I believe you've gotten that.
Yes.
Okay, now we're going to do an example to just write the equilibrium constant of, okay, let's look at this. Okay, now in the course of a chemical reaction, the concentration of gases and aqueous species normally change. The concentration of solid and pure liquids are always constant. Hence, they cannot appear in equilibrium constant expression. Please write this, very important. Please write this. In the course of a chemical reaction, the concentration of gases and aqueous species normally change, while the concentration of solid and pure liquid are always constant. Are always constant. Hence, they cannot appear in equilibrium constant expression. Have you gotten that, please?
Yes.
Okay. Let's see this. I want to give you an equation. So you just write out. Please, you have to annotate this for me. You really have to annotate this. Let's see this. Okay, let's look at this. Correct. All right. I will need you to give me the equilibrium. Just annotate it for me. The equilibrium. Sorry, the equilibrium constant. Yes.
How you do finish? No, you finish.
Okay. And the last one. Just this. All right. This is all. All right. This is awesome. This is awesome. You did perfectly well. Now, so you can actually now write equilibrium constant if you were given such to solve. That's just one of the simplest things to really do. Okay. There's something we are almost done, but there's I think there's one more thing okay, now one thing is what's the importance of equilibrium constant? Please just write importance of equilibrium constant. Importance of equilibrium constant. Number one, okay, that's equilibrium constant. It determines the yield of chemical reaction at equilibrium. It determines the yield of chemical reaction at equilibrium. Now, like what you did something and you got equilibrium to be 1. Now, if equilibrium is greater than 1, that means more product is formed. Now, if equilibrium is greater than 1, that means more product is formed. The forward reaction is favored. Please write that if equilibrium is greater than 1, it means that more product is formed. The forward reaction is favored. But if equilibrium constant is less than 1. That means less product is formed, which is a very bad yield, a poor yield. Now we have a backward reaction. The backward reaction is favored. The backward reaction is favored. Okay, another important thing we should know about equilibrium constant is that it depends on temperature. It changes with change in temperature. All right. Now, there's something we just want to define. Something called free energy, G. Free energy, G. Now, free energy, G, is the energy for doing useful work. Now, there's something we call Gibbs. That's Gibb apostrophe S. Gibbs free energy Now, Gibbs free energy cannot be measured directly, but change in free energy can be measured. Now, change in free energy determines the spontaneity. Change in free energy determines the spontaneity of a given reaction. Change in free energy determines the spontaneity of a given reaction. Now, for a spontaneous reaction, delta G is negative. For a spontaneous reaction, delta G is negative. All right. There's something else I want us to explain called reaction order. Reaction order. Now, the order of a reaction or reaction order is defined as equal to the sum of the powers to which the reaction order is defined as equal to the sum of the powers to which the concentration of reactant I'm going to explain that. Now. Now, what we are trying to say about here is this. I think I have to clear this. Okay, maybe I shouldn't clear this. Let's see. Oh no, I shouldn't. All right. I guess I got what I wanted now. Now, what I'm trying to say is this: we have coming. Now, let's use one of these reaction, for example. Because if the concentration is constant, the order will be 0. Now, let's look at this reaction. How do we get the reaction order? Remember, we said is defined as equal to the sum of the powers to which the concentration of reactants. Okay, now we'll be concerning ourselves only with the concentration of reactant. That means we should be having the reaction rate. We should be having the reaction rate as R is equals to K into, let me use the first one for example, SO2
What is K?
sorry?
K.
K, okay, K means constant. The rate constant, that is K. K is the rate constant. Now, from here now, the concentration, we're only concerned with the reactant. The concentration from what we have just written now, the concentration are raised to the power. Now, how do we get the reaction rate order now, or the reaction order? The reaction order is equals to 2 plus 1, and that gives us 3. So this is the reaction order. This is the reaction order. Now, please write this. For complex reaction, I only did that for number 1, that's A. For A, please write this note. Note, for complex reactions, reaction orders are fractional. Reaction orders are fractional. When the concentration of all the reactants in a given reaction are constant, please write, when the concentration of all the reactants in a given reaction are constant, the order will be 0. The order will be...
Can you what you said?
Okay. Remember I said I started with, for complex reaction, orders, that's reaction order, are fractional, full stop. Then I mentioned another thing again. When the concentration of all the reactants in a given reaction are constant, the order will be 0. The order will be 0. Okay. I'm going to do number 2, so you do number 3. I'll just do number 2, then you do number 3. Okay. For us to do this now, the R becomes the K, the N2, sorry, the H2. So then the order all right. Please just do number C here. Just do C on top there. And just annotate it. I would like to see that. Did you get that, please? All right. Awesome. That's quite good. But there's a UME question from 1999. I would like us to just solve. Okay. I would like us to just solve. I can see that very clearly. Okay. On reaction order, Y giving you Z. All right. They said the rate equation for the chemical reaction above is, they gave us something on minus delta X minus delta X is equal to delta T, giving us K okay, kx squared y, okay. Now the question now is this: what is the overall order of the reaction? What is the overall order? What is the overall order of the reaction? This is a UME question, 1999. Do you think it's something you can try?
Professor, can you repeat the question?
Sorry?
Can you repeat the question?
What is the overall order of the reaction? Answer is 2. You said the answer is 2. Why did you say 2?
Because the
You said?
power is 1. So 1 plus 1 is 2.
Oh, I misplaced. I gave you one wrong information here, and I really apologize for that. Okay. This was meant to be okay. That it was meant to be like that. Okay, so what is the overall order of the reaction? Any idea now?
3.
Why did you say it's 3?
Because the power of x is 2 and the power of y is 1.
Okay, you said the power of x is 2, power of y is 1, and that's making it 3. You would have been correct, but I also gave you something. I said when the concentration of the reactant in a given reaction are constant, then the order will be 0. Since we were not given any one for y, we take that as a constant already. So for x, we're giving us 2. For y, we take it as a constant. Then the answer becomes 2 again. Did you get that?
Yes.
I gave it to you as something to note. That for Y, when the concentration of the reactant in a given reaction are constant, then the order will be 0. Okay, we have really come to the end of our class, but I have lots of assignments to give you. Lots of assignments. In fact, I am really wondering, I know it's something you can do, but let's go back to those questions that we skipped due to temperature. Let's see how we can do them. Those questions we skipped due to, where are they, please? I think I should have them. Those questions we skipped, they should be here now. Okay, let's look at this one. Because I know with pressure, with temperature now, we know how best to tackle that question. And equilibrium constant. You know how to do the equilibrium constant right now. Okay, look at this question. Where we increase the temperature of the reaction, what will happen where would equilibrium shift to? Yep.
So to the left.
To the left. Okay. When we decrease the temperature, where will it shift to?
To the right.
Okay. I can see you're still looking at your notes. Okay. Um, okay. I guess let's see. Oh, let's see something else. Okay, I guess I would I think I'm coming, please. Actually trying to check out for something. Where is this one? Oh, I didn't find what I was looking for. Coming, where are you, please? Okay, I have something that has an answer key. I want us to really check if this is correct. Maybe we just check a few questions there, and if it's correct, you say the person has tried. You can see this, right? You can see this, right?
Yes, sir.
Okay. Um, okay. Look at this question. A decrease in the concentration of dihydrogen sulfide, where will equilibrium shift to?
To the left.
Okay. Increase the pressure of the system, where will equilibrium shift to?
To the To the left.
Increase the temperature of the system. Where will it shift to?
What is temperature?
Sorry?
Can I make a reaction it is?
Okay. It was not given. The energetics was not given. So we don't answer that question. We just say, you just, now we must just assume that heat is a reactant. In this case, it's not even, it's not, okay. We can't, we'll have to determine the energetics of the system. And since it was not given, we really don't know. So we could leave that out. Yeah, now D, increase the concentration of carbon disulfide. Where will equilibrium shift to? Yeah? Are you there?
Yes, sir.
Okay, D, increase the
To the left.
concentration. You know where you know which one is carbon disulfide?
CS2.
Yes, please. So where will equilibrium shift to?
To the left.
Okay. Decrease the concentration of methane.
To the left.
Sorry?
To the left.
To the left. Awesome. So almost everything shifted to the left. I guess next next time we come, we would complete some of these questions. I'm going to send your question to mommy tomorrow. Please, if I have not sent it tomorrow, please do send me a message via WhatsApp. I can't send it now because it's quite dark here, and I need to snap it. I want to snap. It's written somewhere, or I want to extract it from a textbook. So I have to snap it to send to her. So that why the day is brighter tomorrow, I'll be able to snap it and send to you tomorrow. Do you understand, please?
Yes, sir.
All right. Wow. Any question?
No.
Okay. So we'll be able to treat all these questions next time we meet. We'll be able to treat all these questions and okay, I think I have another question I'm seeing here. We'll be able to treat all these equilibrium constant questions. They are awesome. They are awesome. They are not difficult. Something we have been doing together and something we can do again. All right, let us pray. Father, we thank you for today. Thank you for how far you've helped us. Blessed be your holy name, Lord. In Jesus' name.
Amen.
Amen. All right. Have a wonderful night. Bye for